In our this topic of multiple linear regression model. So that is the same example I will try to take, which I took earlier, that we have 20 students and we want to model their marks with respect to the variable number of, say, hours of study, number of assignment, and number of hours what they have played. So the same example, same data set. So what I did in the last lecture, I just considered only here these two things, y and x1, and I considered only one variable. But now I will try to consider all the three variables together. And now you have to understand that how this univariate is being extended to a multivariate setup, what type of things
गंदी बात।
happen.
चलो पानी
So
चलाओ,
on.
चल के मुंह करनी, पानी चलाओ,
Right.
पानी चलाओ, चल पानी चलाओ।
So definitely, as I said, means that the difference between simple linear regression model and multiple linear regression model is very simple. When you are trying to consider only one independent variable, then you have simple linear regression model, and when you are uh, trying to have multiple linear regression models, when you have more than one independent variable, then you have multiple linear regression model. Yeah, friends, I'm sorry. Means I have to take some liquid during my this lecture because after this COVID, my throat and mouth gets dried badly within a minute or so. So I have to keep it wet to talk to you. So I hope you won't mind taking water, tea, or juice during the lecture. Right. Okay. So anyway, so this multiple linear regression model is going to extend the simple linear regression model in a way that it will allow the average value. Means earlier you had expected value of y is equal to beta 0 plus beta 1 x. Now it will extend to more number of independent variable, more number of explanatory variable. Okay, well, one thing I can clear here, that sometimes I use the word independent variable, sometimes I use explanatory variable. So these are different terminologies for the same thing, right? And so sometimes we use steady variable, explanatory variable. Sometimes we use dependent variable as y and independent variable x. So don't get confused. Right, means I do it intentionally so that you get familiar with as many as possible terminologies. Right, and then the second thing will be that definitely when you were trying to consider the simple linear regression model, you had here one relationship between x and y, but now you have here x1, x2, x3. So possibly you can plot into 3-dimension, 4-dimension, 5-dimension. So different types of shapes will come into existence. That when you have only one variable, this was a straight line, but when you have two variables, possibly that may become a sort of surface. In 3-dimension, that may in 2-dimension, and in 3-dimension that may become a sort of volume, etc., etc. So when you are trying to extend it, so this will allow to consider more than one shapes. It means beyond a straight line also you can consider different shapes of relationships. Right. Okay. So now if you try to see, I will go very simply. You had considered y equal to beta 0 plus beta 1 x as a simple linear regression model with one variable. Now I'm going to extend it for x1, x2, xk. So I can just write in general as say y is equal to x1 beta 1 plus x2 beta 2 plus xk beta k. I'm not taking here beta 0 because if you want here beta 0, you can just take this value x1 to take value here 1 always for all the variables. Right, so beta 1 will act just like an intercept term. Because my objective is this, I want to express this model in a compact way. So that is why I am doing it intentionally. So you can see here that the way you had written x beta earlier, I have just extended to x1 beta 1 plus x2 beta 2. So now you can see that here beta 1 is indicating the slope parameter associated with x1. So the value of beta 1 will be indicating the partial change in the value of y with respect to x1 variable. And beta 2 will be indicating the average change in the value of y with respect to x2 variable, right? So that will be sort of extension. Right, okay, so this beta 1, beta 2, beta k, they are the regression coefficient in general. Epsilon is the same quantity random error component that you did earlier. Right. So, and it has the same concept. And surely when you are trying to go with the multivariate setup, there are more reason for the epsilon, because sometimes there is an interaction effect of the variable that also comes over there. and because of which you have to take care of the random error, right? And if you assume that expected value of psi is 0, so as I said, if you try to see here, beta j is equal to partial derivative of expected value of y with respect to xj. That means what is the interpretation? This is the rate of change in average value of y with respect to xj. That means if you make one unit change in the value of the jth independent variable, then how much the average value of the y will change. Remember, all the interpretation are with respect to only the average value. Average means if you try to repeat the experiment for a couple of times, then on an average this is going to happen. Right. So now what I try to do here means I try to now conduct an experiment, but the only difference is that I have here more than now one independent variable, x1, x2, xk. So what I try to do, I choose one value for x1, one value for x2, one value for xk, and based on that, I try to observe the value of here y, which is indicated here as say y1. So this is actually one set of observation y and x1, x2, x up to xk, right? So so as earlier you had taken only x comma y, so now this will be x1, x2, xk comma y, right? So and then these small x, these are some numerical values. For example, I can say, okay, if a student has studied for 5 hours, he has submitted 3 assignment, and he has played only for 8 hours, then what are the marks, like as here y? So you try to collect this data, you try to conduct this experiment, and we assume that this is our linear model which in which we are going to be interested. Now, as soon as we say we are interested in this model, that means our objective is to know the value of beta 1, beta 2, beta k. And now I am sure that you must have observed in the last lecture that initially I said modeling, but finally what I did, I simply found the value of beta 0 and beta 1. That means what? That whenever we say modeling, modeling is equivalent to finding out the values of the parameters, that how the values of the parameters can be estimated on the given set of data, and that is actually modeling. Means modeling one aspect of the model, and after that you have to check, verify, there are other things, but then estimation is one of the most primary important part of any statistical modeling, right? So I assume here that all this data set, they are going to follow this model, and if you try to translate it to your given example, right? So we have here these three variables, and now you can see here that these are the variables of something like here x11. For example, you have taken here x11, x12. So this is going to be here x12, this is going to be here x13, and this is going to be your here y1. And similarly, you have obtained, and now you can combine all these values in the format of a vectors and matrices. So you can see here, this is here a matrix which I have framed x1, x2, x3. All these observations, whatever are here, for the x I have written here, and for the y I have written here. So you can see here this y is here a 20 by 1 vector, and x here is a 20 by 3 matrix. Right. So x is a matrix containing all the observations on the independent variable, and y is a vector which is containing the observations on the study variable, output variable, response variable. Right. So that is what exactly I'm trying to show you here. Now in theory, I try to translate. I assume that whatever this observations we have obtained here through our experimentation, each of them is going to follow this model. They are going to assume the form of this model. So that means each of them will satisfy that equation. So you can see here, I have written the same thing for each cut of this observation. And now after that, you have learned that how to write different equations in the form of vectors and matrices. So that we are going to do here. So you can see here from here to here, I have simply written all these an equations in the form of vectors and matrices. So this matrix I'm writing here as a x, this vector here as a beta, this here as epsilon, and this here as a y. So I can write down this entire model very compactly as y equal to x beta plus epsilon. So you can see here that capital X here is a matrix of order n by k of all the observations on all the independent variables. Y is a n by 1 vector of all the observations on the steady variable, and epsilon is a n cross 1 vector of all the random error components, and so I can write down this model. All right. So that is exactly what I have written here, but clearly. Right. So, and yeah, means as I said, if you want to have intercept term here, you just have to put the first column to be here 1 1 1 1 1, and that will be your intercept term. Now, we make here some basic assumptions. Well, whenever I try to expose these basic assumptions, and the first question comes here: why should I do it? Why they are needed? So, and then particularly for those people who are not coming from mathematical or statistics background, for them it is difficult to understand. But then my question is very simple. Now, means if I take the most recent example of COVID, then now you can see what's really happening, that if somebody is going for the RT-PCR test, many times this RT-PCR test is giving you a negative report, whereas the person is positive. So what is really happening now, people have understood that this type of variant, this is caught by this RT-PCR test only when somebody goes after third or fourth day. It's otherwise it will not catch. And so what is that? So now when somebody is going to go, for the RT-PCR test, the basic assumption is that he or she has to wait for at least for 3 days. Only then this RT-PCR test will give you a proper result. That is an assumption. These assumptions we are following in the day-to-day life, but as soon as we come to this mathematical assumption, people get do scared. But that is the same thing. I will try to explain you that this is only a mathematical thing. For example, a doctor will make a one tablet, say at AD or BD, something like this, right? That means after dinner or before dinner. So you understand what is the meaning of AD, BD. So similar are these assumptions. So these assumptions are the need, because whenever we are trying to do some statistics, we need some mathematical tool, and those mathematical tools are applicable under certain conditions. So that is why these are the some assumptions what we make, but they have some interpretation also. And in practice, it is possible that many of these assumptions may be getting violated. So at this moment, I am going to assume that all these assumptions are correct, and then how to do the modeling. But surely, when these assumptions are validated, then we have different types of tools, and we try to play with them, and we try to employ them. And that is why this regression analysis, that is a full semester course at my place, where we teach it in, say, 45 to 50 classes at least. And Abhay has given me only 3 hours, so I can't help it. So Abhay is responsible if you cannot understand anything from here, right? Anyway, so let us come back. So UCC, this is very simple assumption. This means the average value of epsilon is 0. So obviously, when you are trying to collect the data from a population, there is going to be some random error in every observation. Sometimes the values are going to be more than the true value. Sometimes they are going to be smaller than the true value. So you assume that whatever are those random error plus minus, but on an average, they will be equal to 0 in the population, right? That is acceptable. Then this is the covariance matrix of this random error component. You assume that each of the random error has got the same variability, and all these random errors are independent. Independent means whatever I am doing here, that is not going to affect the other person. Right. So that means, so that is the idea. Then rank of x is equal to k. That's the mathematical expression, but the simple interpretation is that all the variables what you have considered in this matrix x, x1, x2, xk, they are all independent. For example, if I say you choose three variables, say here income, expenditure, and saving. Now you try to take them as x1, x2, x3, but don't you think that income is equal to expenditure plus saving? So these variables are not independent. So this is what we mean to say when we say the rank of x equal to k. We are assuming that all the variables are mutually independent of each other. That means the occurrence or non-occurrence of one variable does not affect the other. So that is what we have to keep in mind. And x is here a non-stochastic metric. That means the observation what you are assuming, what you are considering on x, they are fixed values. They are not random values. So the advantage of this is that in case if you try to conduct an experiment in New Delhi or in Kanpur or in Calcutta, you assume that the observations are going to be similar. Means you know that in medical people try to conduct clinical trials at different places. So this assumption will help at this moment, and then after that we are simply assuming that these randomers are following a multivariate normal distribution with mean 0 and covariance matrix sigma square. So that is needed when you are trying to build up the confidence interval, test of hypothesis, etc., etc. So the moral of this slide is that these assumptions are needed at every step, and if these assumptions are violated, then whatever we are going to understand here that will not remain true. So now, do you recall that in the last lecture we had written our model if y equal to beta 0 plus beta 1 x plus epsilon, and then we have written here is for each of this xi, and then we had multiplied here with this, we have minimized this quantity summation I goes from 1 to n epsilon I square. The same thing I try to do here also. You can see here that we have here epsilon 1, epsilon 2, epsilon n. So we try to compute this quantity summation epsilon I square, and then I try to minimize it. So in the last lecture, I had used the principle of maxima and minima, and I had partially differentiated it with respect to beta 0 and beta 1, and then we had solved it. So a similar process we also do here. And but I'm not going to give you the algebraical part, but the way you had obtained the values of B0 and B1 in the last lecture, now we can obtain here the similar value here B. So B is the value of beta. So beta you can see here the way you have defined here. This is a vector quantity beta 1, beta 2, beta k. So similarly, this B here is also here a vector B1, B2, Bk. So this B1 is going to give us the value of beta 1, and Bk is going to give us the value of here beta k. Right. So this is not a scalar quantity, but this is a matrix, and this is actually a vector of order a by 1. And you can see here that when I am trying to make this assumption here, I have introduced here one more parameter, sigma square, which is the variance of the random error. So obviously, means if I say that in any model, if the value of the random error is small, then the model is definitely going to be better. And if the value of the random error is quite high, then the modeling is not going to be good. But this variance is in the whole population. We don't know its value. So we are always interested that, okay, we have done the modeling, but how much is the random error involved in this one? Right. And this statement is something like this. Suppose if you have two friends, and suppose one of the friend has a habit, but if you call them for a cup of tea at 5 o'clock, one friend will come say at 5 o'clock plus minus say 3-4 minutes, and then another friend he will also come at 5 o'clock, but sometime his delay or say mean the time of arrival is varying with by say 30 minutes. So that may come at 4:30, that may come at 5:30. So definitely, what you will say, you have more confidence on the first friend whose variability is less, because there is a smaller random variation. So that is the same thing we also try to do here, and we would like to know the value of this sigma square on the basis of given set of data. So this value is going to help us. So if I try to obtain this value here, sigma square hat, and if you can see here, this can be obtained very easily. For example, this here b, you know the value of x, you know the value of x, you know the value of x, you know the value of y. So you can simply compute it. This is only matrix computation. But anyway, you don't have to do it. Your software is going to help you, and it will give you the numerical value. So you have to mainly understand that how this value is obtained and what is the interpretation. So you know here the value of y, you know here the value of x, you know here the value of b, you any the number of observation, k the number of variables. So you can estimate, find out this numerical value of this random variation also, right? So as I explained you in the last lecture, that we are trying to minimize this vertical error. So the same thing we are doing in this multiple regression case also, but I cannot show you here on the screen just like I have shown you it in the case of 2 dimension. Now we have here k plus 1 dimension, so I cannot plot it. So that was the reason I was saying again and again that in the first lecture we are trying to create the foundation, and we are going to implement it in the second lecture. So as you had obtained the fitted model in the last lecture, what you did, you obtained the value of beta 0 and beta 1 as b0 and b1 respectively, and you substituted those values there. So the same thing I am doing here also, that I have here the model y equal to x beta plus epsilon, and then I am simply trying to replace here this beta by here b. So this is becoming here my weighted model. Sometimes people get confused that where this epsilon has gone. You see, you have obtained the value of b in such a way such that the value of the random error is minimum, and the minimum value of the random error is 0. So that is why I assume that this value of b has been obtained such that all the epsilons are 0. That is the ideal condition. So that is why this is your here the fitted model. And if you try to take any given value of your x, and if you try to substitute it here, it will give you the fitted values, right? So just like you had obtained the value of the value of y after substituting the value of x, and you had obtained the residual. So earlier residual you had obtained that as a difference between the observed and fitted values. So the same thing I will do here also. This is my observed value and this is my fitted value, and I try to take the difference of the two, right? So this is the residual, but the main difference is that this is here the residual vector. Why? Because you can see here this y here is a say n cross 1 vector, n cross 1 vector y hat. So this e is going to give you here a vector quantity like I said e1 e2 en. So that means this vector will give you the value of residuals corresponding to each of the observations. Right, okay. So now we come back to our original example and try to understand it. So as I did, it means earlier, means I'm not confident whether you know at this moment this R completely. But if you, that's my just suggestion to you all. Means if you want to learn this R quickly, on this NPTEL site, I have a 20 hours course on Introduction to R software. That's a very elementary course. You can download the videos and possibly you can take the help. Right. So means I believe that you know R, otherwise means I cannot proceed further. So there is a command in the R software, see here LM, in which you have to give formula. There are many things, but I'm not bothered about those things at this moment. So using that command, I try to get here the model. But now here comes another trouble. Means earlier you had plotted x and y, and you had observed that x and y, they are more or less linear. But now you have here three variables. So now, and then you have decided that the model is going to be linear only when it is linear with respect to the parameters, not with respect to the parabola. So that means, sorry, variable. So that means even if you have parabola, you can fit there a linear model. So don't judge the model by the shape of the scatter diagram. Right. So now my question here is this: we have here three variables, and somehow we want to ascertain whether the joint relationship of y with respect to all x1, x2, x3 is this relationship is linear or not. Now, means how to do it, that is a big challenge. And if I have suppose a 20 variable, then how are you going to do it? One variable y and then x1, x2 up to here x20 with 20 variables together. How are you going to see that the joint relationship between y and x, this is linear? So that is the big challenge, but up to certain extent we try to do it. So this is called here a scatter plot. The scatter plot, what we try to do, we try to plot uh, all possible combination. We have here y, and see here x1, x2, x3. So we will try to plot between y and x1, y and x2, and y and x3, and we try to put it in a single plot. So this is called here a matrix plot. So you can see here, this is here y, you can see here y, this is here x1, x2, and here x3. So, and yeah, same thing here also y, x1, x2, x3. So now this is here a plot between y and x1, and this is here a plot between y and x2, and this is a plot between here y and x3. And yeah, means similarly, means this is a plot here between x1 and x2, and this is a plot here between, see here, x2 and x3. So anyway, now from this from this matrix plot you can judge, uh, say the relationship between y and x is linear or not. You can say this is quite linear, right? That we did in the last lecture also. Yeah, for y and x2 it is little bit tricky affair. For y and x3 this is quite linear. But the moral of the story is that just by looking at these three curves, you cannot decide whether the joint relationship of x1, x2, x2, x1, x2, x3 with y is really linear or not, because we are not considering here uh, the interaction effect. Means definitely, if in the means agricultural experiment, if you are trying to give the quantity of fertilizer and say rainfall, both are correlated. Means if there is a high rainfall and low fertilizer, the crop will actually get it destroyed because of rain. So this is so there's an optimum value of the irrigation, optimum value of the rainfall, fertilizer, etc. So they are actually interrelated, but we are assuming it to be uh, independent. So all those complications are there. But I always say we all are human beings. We have to move forward. Means otherwise there is no difference between a human being and other creation of the God. So we will try our best. So I assume that, okay, if I can say, see here that the relationship between y and x1 is linear, y and x2 is linear, y and x3 is linear. So I can believe that, okay, their linear combination will also be linear. But surely it is not 100% guaranteed, because there can be interaction also. But in spite of all those things, we have to find a solution. Right. So suppose we now take here, and then yeah, once you are trying to look at x1, x2, x2, x3, that will also give you an idea whether the independent variables are really independent or not. Right. So anyway, we decide that, okay, this relationship is linear, and we try to find our model. So once we try to find our model here, is I have to use this type of command here, and our model is actually y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. So I try to give here, and I get here this type of outcome. So now you are going to write down. You can see here, this is the value of intercept term. This is the value of beta 0. This is the value here x1. So this is the value of here beta 1. This is the x2. This is the value of here beta 2. This is here x3. This is the value of here beta 3. So I can write down the model here, y is equal to 8.769 plus 1.997 beta 1 x1 plus beta 2 x2 plus beta 3 x3. So you can see here, by looking at this outcome, you can find out the model. Right. Okay. And yeah, means if you try to see, if you simply want to see these coefficients, if you want to know only coefficient, then you have another command here, coefficients. So it will give you only the value of the coefficient. The more important part which I want to show you here is that you are getting these four values. What are those four values? How they are coming? So these are the four values of actually here B, which we have computed from here. And these values are here B0, B1, B2, B3, and which are obtained here like this. So it is very important for you to understand that how these values are found and what are they indicating. So now you can see here, we had understood that what is the value of B1 indicating, that is the average, rate of change in the average value of Y when there is a unit change in the value of X1. This is the value of here B1, and similarly for B2 and B3 also. And if you want to know the fitted values here, then in R you have a command here, fitted dot values. And if you simply try to give it the same command like this one, you will get here these 20 values. So these 20 values are the values which you have obtained on the basis of the model. So you can see here, these are here first, second, third, fourth, up to here 20 values. First value is here 180, 116, 117. So if you try to recall your here this data set, so what you are saying, this is what you are observing in real life, these values of your Y, and now you have obtained here the model in which you try to substitute these values of X1, X2, X3 and try to compute the values of here Y, which are given by here fitted values. Right. So you can see here, this is the screenshot. I just took the screenshot so that you can believe on me that these things are really happening and how it will look like when you try to do it on your own. Right. Similarly, you can find out their residuals. Residuals are obtained by simply this command, residuals. Inside the parentheses, you have to write the command, and you will get here 20 values. So these 20 values are giving you the value, the difference between yi and yi.